Okay, so welcome back to another video. So here today we have an infinite sum of the Riemann Zeta of 2n subtract 1 with our index starting from n is equal to 1 and then all the way up to infinity. So if you've watched blackpenredpen's video on evaluating the infinite sum of the Riemann Zeta function, the format is similar, since in his video he evaluated the sum of the Riemann Zeta at n, but the index started at n is equal to 2, since of course n is equal to 1, that actually diverges for the Riemann Zeta of 1. But here we're dealing with n is equal to 1 for 2n, so our inputs are dealing with, even terms, positive terms. So in a similar format for solving this, it's actually very familiar in how he did it in his video, but of course, eventually when it comes for this problem, it's gonna take quite a bit of a term, like I'd say somewhere near the end of, throughout that process. But it's not just only that we're going to solve in one way, we're actually going to solve in two ways. Well, that first method is in the similar format I just mentioned, but then the second is we can apply using the gamma function relationship and then showing that the value is the same as just like solving it from the first method is there. Nothing more to be said because, well, there's going to be, of course, you're going to see a bunch of, formulas and a couple, series, representations that we can actually utilize and use for both ways, especially. So I don't want to give too much. The second way is actually, personally, I think is the most interesting. The gamma function is especially. So you'll see what happens from there. So anyways, let's just jump right in. So if we start with the definition of the Riemann Zeta function, it says, so zeta of n, for some input n is actually just equal to the infinite sum. S is equal to 1 of our index of 1 divided by s to the power n, such that, of course, for the real part of n is actually strictly greater than 1. If we utilize that, then we could just make that substitution back in to our, our given. So the infinite sum, so from n is equal to 1, then we sub this back in. So this is going to be infinity. Over here, s is equal to 1 of 1 divided by s to the power 2n, and then still subtract 1. To make things a little bit interesting, now, of course, I think anybody who has seen the video would know where I'm going. blackpenredpen's video can see where I'm going with this, but we're actually going to be doing a little bit of a reindex. Inside the parentheses, I can actually start from n is equal to 2, but I have to evaluate it at the term for n is equal to 1. So let's see, if we go back to just rewriting this step again, so that means if I reindex this is s is equal to 2 of 1 divided by s to the power 2n. Then that means I have to evaluate this for the term at s is equal to 1, which is just 1. Then we subtract 1. And then just like that, the terms cancel each other out. So that gets rid of that. So now all we're left with is, well, and then you can actually see from this notation over here for these two sums in our series we evaluated, you can see that this is perfect, that we can actually apply a geometric series, but for doing so, we can actually interchange the order of the sum. So now the s will come out outside, and then, so s is equal to 2. Then inside this is the infinite sum, n is equal to 1. Of 1 divided by s to the power 2n. Now, if we see that I said that this is a geometric series, because even with this common ratio of course, the absolute value of some ratio x has to be strictly less than 1, but dealing with our index for s is equal to 2 and so on and so forth, it still lies within that boundary, so we can still apply that rule. So what this means is that now, just from fixing all this, so we can write that the infinite sum, or with the geometric series, is equivalent to just saying this is 1 over s, put that same notation over here. So then in here we'd have that our index starts at n is equal to 1, not 0. So that means the numerator is not 1. It is instead 1 divided by whatever the ratio is, or it's the ratio, and then divided by 1 minus that ratio. So that would be 1 over s square, and then divided by 1 subtract 1 over s square. To make things a little bit easier to get rid of the fraction, so I'll just multiply a s squared to both the numerator and denominator. And so now we have the following. So s is equal to, and then this will just be 1 divided by s squared subtract 1. But as you notice from down below, the denominator can be factored out because it's a difference of squares. So we actually have to deal with some for the next step, dealing with partials of partial fractions. So we would have now over here, this is just s plus 1 and then multiply by s subtract 1. Then if we just, of course, apply with, the fraction decomposition over here, if we just say that this is some constant a divided by s plus 1, add this with b divided by s minus 1, set that equal to the numerator, then we see that if we just do the cross multiplying, so a times s subtract 1 plus b times s plus 1, set that equal to 1, then you'll see that we have our following constants. A, if you just solve for each, plug in the s's so that 1 will cancel out with a 0. So now that we have that a is equal to -1/2 and then b is equal to just +1/2, then we see from here that now we can actually have, the new sum. So what I can do from here, this is, let me put back the constant back into, what we saw back into our, decomposition right here. So now this will be -1, then we divide this by 2 times s plus 1. Add this with 1 divided by 2 times s subtract 1. So that's what the composition comes down to. We just substitute this back in. So don't forget, we can also factor out a 1/2, and since it's minus, I'll just interchange the sum. So this will come first and then this will come second. So now we have 1/2, then multiply by the infinite sum of s is equal to, then inside the expression, so this is s subtract 1, and then we add this, or rather subtract, with 1 divided by s plus 1. And so from here, so let me actually switch the markers. From here, we can actually just apply the continuity over here and say that we can actually write this as a sum of two, infinite sums. So, well, half and then another half. So half times the infinite sum from s is equal to, and then we just apply this for 1 divided by s minus 1, okay? Then now do the same thing, so distribute that 1/2 and then apply that continuity again, so it's 1/2, and then multiply by the infinite sum, so s is equal to, of 1 divided by s plus 1. Now things are a little different from the video you saw, so how can we actually approach this? So interestingly, what you'll notice is that we can actually apply some substitution, but before we do that, here's something to make an observation of. We can see that the following infinite sum with k is equal to 4, for example, for this index, of 1 divided by k subtract 1 is actually just equivalent to the infinite sum where our index instead starts at k is equal to 2, but we have a different series. Instead, it's going to be 1 divided by k plus 1. You can actually, obviously see this if you were to expand the sums itself, and then it's exactly the same. So where are we going with this? Of course, we're actually just going to do that substitution once again. So now implying with this means now we have the new 1/2. Now this is the infinite sum. We just replace the k is equal to 2 over here. Well, actually, this is the k, we replace the this with for here, but we also have to evaluate our terms for 3 and 2. So now s is equal 4 of 1 subtract s minus 1. So we have to evaluate for 3, which of course that's add this with 1/2, and then 2, which is just 1, so plus 1 plus 1/2, and then now just substitute, or well, not yet. Now we have the infinite sum from s is equal to, and then 1 divided by s plus 1. Okay, so from there, now we could actually just combine these sums together. So, these two terms together, so that'll be just 3 halves. But then we also have a, using this, observation right here. So of course we can actually just make this substitution. So this is just 1/2. Then let me write the 1 plus 1/2 out term first. So 3 halves. Make this substitution for here. So now we'll replace this with plus the infinite sum of s is equal to of 1s plus 1, and then minus the infinite sum of s equals 2 of 1 divided by s plus 1, and then you'll notice that these two infinite sums, they just cancel each other out just like that. And so all we're left with is just to make the following calculation, that 1/2 times 3 over 2 is indeed just equal to 3 over 4. Just like that, we are done with the, I guess you could say, the easy method, or the blackpenredpen method, if you want to put it that way. So this is what it comes down to. So 2n, the Riemann Zeta 2n minus 1 of the infinite sum is actually just going to equal the finite value of 3 over 4. So with that, let's actually move on to the second method. Okay, so now the next method is, as I mentioned, we're actually going to be using the definitions with gamma functions. But to actually start, let's actually define what the Riemann Zeta function is equal to in terms of the gamma function. So with that, we know that the Riemann Zeta of S is equal to 1 divided by gamma of some input S, and then this is multiplied by the improper integral of x to the power s minus 1 divided by e to the power x subtract 1 dx. I think it's also worth noting that we should also put the formula for gamma itself. So gamma of s is indeed just equal to the improper integral 0 to infinity of x to the power s subtract 1, then multiplied by e to the negative x, okay, and then times dx. So from here, now we're just going to make a bit of a substitution. We have to substitute the 2n for our zeta over here in terms of the gamma. So now let's actually do that. So by applying so we have the Riemann, or the infinite sum, n is equal to 1. Then we just make the plug in the stuff. So 2n over here. So now this will be 1 divided by gamma of 2n. Then multiply with the the improper integral. This is, so x to the power 2n minus 1. Then we divide this by e to the power x subtract 1 dx. This is going to be a very interesting take on this because we have a minus 1, but we actually want to be a little bit clever with this. And you'll see, and you understand why I wrote the gamma of s in terms of this definition. So we can actually write another way of 1 by writing as 1 divided by gamma of 2n, then plug in the gamma of 2n over here because it still retains that, that identity. So here, what I can put is, now this is subtract 1 divided by gamma of 2n. Then we multiply by the improper integral from 0 to infinity of x to the power 2n minus 1 multiplied by e to the negative x dx. All right, pretty clever trick, right? We need to figure out how to calculate this, this entire expression over here. So let's actually work on doing that. So we notice that, of course, we can factor out, well, it's not only that, we can also apply with linearity. So we can put this under one integral, of course, the improper integral. We can factor out the 1 over gamma of 2n, the integral depends on x. So now we would have just 1 divided by gamma of 2n. Then we multiply by the integral from 0 to infinity. We notice that they both share x to the power 2n minus 1, so I'll put that outside. And then with differences over here, so now we would have a 1 divided by e to the x subtract 1, and then subtract with 1 divided by e to the x, then dx. What you'll notice is, well, we can actually fix this up a little bit and get a common denominator for the inside expression over here. So we see that just providing the same thing again. So gamma 2n, proper integral, then x to the power 2n minus 1. Then we see that this is just e to the x just cross multiplies, e to the x subtract e to the x, and then that'll be positive 1. So it'll be 1 on the numerator. Then we divide this by e to the x and then multiply by e to the x subtract 1. What we can do from here, well, now let's actually just plug this back into our infinite sum. So at least we have something, simplified. So n is equal to 1 of 1 divided by gamma of 2n, then the proper integral, x to the power 2n minus 1, then 1 divided by e to the x divided by e to the x subtract 1, then dx. Interestingly, you'll notice that due to absolute convergence over here, we can actually just interchange the sums. So anything with the dx can actually just come outside, and then anything dependent with the n. So let's see, we have an x to the power 2n back here, so we'll just move that outside as well. So this means that, again, just interchange the sums. So we can put this as the proper integral. Now I'm going to write this as dx and then divided by e to the x divided by e to the x subtract 1. Then we multiply this by the infinite sum, n is equal to 1 of x to the power 2n minus 1, and then divided by gamma of 2n. Now this is a very interesting way to approach on how we should be asking ourselves, how should we approach this? So let's actually move on to that. So if we're actually paying attention to evaluate this infinite sum that's in the blue parentheses, so infinity, n is equal to 1 of x to the power 2n minus 1 and then divided by gamma of 2n. So you might be thinking, how are we supposed to do this? If you notice that we can actually write this in terms of a factorial, so we know that specifically that for gamma of s, we can write this as s minus 1 factorial, and then we just substitute this down below with the different input as well. So now we have the infinite sum n is equal to 1 of x to the power 2n minus 1, then divided by, now in this case, this is supposed to be, now this is 2n minus 1, then factorial. What you'll notice is that this is actually a series representation for the hyperbolic sign of x. Now we could substitute this back in over here if we want to, but that's probably going to make things a little bit more challenging and a little bit, of a bit of a mess and, chaotic. So because we are dealing with exponential functions, we can actually use the exponential function representation of the hyperbolic sign, which that it says that this is equal to e to the power x, subtract e to the negative x, and then divide this by 2. Okay, so with this, so now let's actually just plug this back into our, representation. So here we usually have the integral from 0 to infinity of dx, then divided by e to the x multiplied by e to the x, subtract 1. Then we just substitute this back in for e to the x, then minus e to the negative x, and then divide by 2. Now, if we want to, we can actually factor out the e to the x from the numerator. This way, that if that's the case, then we can cancel both the e to the x from both the numerator and denominator. And because with the constant 2, or on the denominator, or rather 1/2, we can actually factor that outside. So by doing so, we can have the following new integral. So this is going to be 1/2, then times the improper integral from 0 to infinity of the following. So we have 1 subtract e to the negative 2x, and then this is being divided by, well, hold on, let me fix that. There was really no need for the parentheses in this situation. And then in the bottom, we have e to the x subtract 1, then dx. So I would usually say that I would leave this as an exercise, but I thought this was a really cool integral to calculate. So instead, we're actually going to calculate this together in this video. So let's actually do that. So we can see that 1 minus e to the negative 2x, if they share the same denominator, we can split this up into a difference of 2 fractions. So we write that as 1/2, then times the integral 0 to infinity. So we have 1 divided by e to the x subtract 1, then subtract e to the negative 2x of that same denominator. And then now all we have to do is just calculate these 2 integrals. But I think before we, I think the most easier, I wouldn't really say easier, but I think the better sufficient approach to do this is to look more towards as an antiderivative, rather find its indefinite integral. We want to worry about the bounds till later at the end, of course. So of course, we're actually going to find the antiderivative of these 2 functions over here. So let's actually start with one at a time. So we're going to start off with 1 divided by e to the x minus 1. So in this for this antiderivative here, you can actually write this as the following. We can write that as e to the x and then divided by e to the x subtract 1, but then subtract 1 as well. So it's e to the x minus 1 for both the top and bottom. So in other words, it just cancels the e to the x itself and then 1. So we still retain that same identity over here, which is okay. So it's just another, rewritten form. But obviously, if we, take the antiderivative, this is easy to see. This is just the natural log of, I'm going to put this in, absolute values. So e to the x minus 1, and then subtract x. Okay, so that's 1 down. So now we have to find the other antiderivative. So this one's actually going to be an interesting one because from here, you actually have to do the u substitution over here. So suppose if we let u equals e to the power x. So by, differentiation both sides, so this is just e to the x dx. But unfortunately, there's nothing we can plug in to do that substitution. So suppose that because we set that u is equal to, e to the power x, just substitute this back in, divide the u. And so we have that 1 over u du is equal to dx. Then, of course, now we could just apply the, substitution. So this will be, u to the, so let me write this. This will be u to the negative 2, then divided by u. Then substitute this back in, so u minus 1 du. In other words, just, simplify this even further, we have 1 divided by u to the cube, then u minus 1 du. So now the next step is, obviously, I'm sure you can see that this is actually a partial fraction decomposition, but it's pretty straightforward to do this. So I'm actually just going to skip that step. If you want to, check and verify yourself, feel free to. So now if we notice that this composition over here, so from this decomposition over here, we would have that 1 divided by u cubed, then 1, or u minus 1 is simply just equal to negative 1 divided by u minus 1 divided by u squared minus 1 divided by u cubed, and then minus 1 divided by u plus 1. Just from that decomposition, so now we just have to, find the, antiderivative. So take the integral for each one and then for both sides. And then now you'll see that the following is that afterwards, the integral from 1 over u cubed, then 1 minus, or u minus 1 du, simply is just equal to negative ln of u, then add this with 1 over u, add this with 1 divided by 2 u squared, then add this with ln of u plus 1. And so now we just plug in back the e to the x. So in other words, just say this is e to the x or over here. So we would have negative x, since ln of e to the x is just x. So now we would have 1 divided by e to the x, add this with 1 divided by 2 times e to the 2 times x, and then add this with ln of e to the x plus 1. Okay, so from here, we just established that this is going to equal, so I have the red underlined with this, and then over here, this is just going to equal this, just like what we did over here. So now if we notice that we just combine these, subtract the 2 together, you'll notice that this will cancel, and that cancels, the minus x minus plus x, this cancels, then all the these last 2 terms will actually just turn to be negatives. So that's great. And so now this is actually makes the simple calculation and say that now we have 1/2 and then multiply with now negative 1 divided by e to the x, then subtract 1 divided by 2 times e to the power 2x from infinity to 0 to infinity. But this is very easy to see. Infinity over here, you have a 0, then a 0. So that's out of the way. You plug a 0 over here. So this is just negative 1. So 1/2 then times negative 1, then 0 over here. So this is minus 1/2. Well, and then it also changes back to the positive since it's a minus. So now this will be plus and then plus. Then over here, now this is actually just 1/2 times 3 over 2, which indeed you do the multiplication, it is equal to 3 over 4, just like that. And we are done. We actually shown this in 2 ways. One with just, using the Riemann sum or the Riemann Zeta function of, the summation definition, and by using the other method with the gamma function, just like that. So the gamma function personally, I think is my favorite. So that's why I wanted to show it in 2 ways. So yeah, that's pretty cool if you ask me.